Wolf Creek Dam in Kentucky is leaking, and not just a little bit. This earthen structure, holding back 722 billion gallons of water, has been hemorrhaging through its limestone foundation since 1968. The U.S. Army Corps of Engineers classified it as high risk for failure, requiring emergency measures to reduce an imminent risk of human life. But here's what makes this story so unsettling. Millions of people downstream have no idea they live in the shadow of a dam that, if it fails catastrophically, could kill between 50 and 120 people instantly and unleash a wall of water that would send damage cascading across 3 states, totaling $6 billion in destruction. This is the Wolf Creek Dam story, a catastrophe waiting inside a secret that America's engineers have been fighting for decades. In 1957, the U.S. Army Corps of Engineers finished Wolf Creek Dam across the Cumberland River in southern Kentucky, just outside Jamestown. The ceremony was probably formal. Speeches were given. Engineers took photographs. The dam was supposed to last forever, or at least for the 100-year design life that engineers projected. They built it to store water, generate electricity, and control floods. The Cumberland River would be tamed. Water would be managed. Disaster prevented. On the surface, it seemed like a triumph of American engineering. But beneath the 256-foot earthen embankment, underneath millions of tons of clay and rock, lurked a geological nightmare: karst limestone. This type of rock is like Swiss cheese. It is riddled with holes and passages. Water dissolves it. Cracks form. Holes expand. Sinkholes develop on the surface. And in 1968, just 11 years after Wolf Creek Dam opened, workers discovered the problem that would define the next 60 years of this dam's existence: seepage. Not a few drops, not a minor leak. We're talking about groundwater actively finding pathways through the limestone foundation, carrying sediment, eroding channels, widening caverns underground. Sinkholes appeared downstream of the dam. Muddy water flowed through the outflow channels. The dam was literally bleeding itself to death through the rock beneath it. Engineers realized they were watching a geological disaster in slow motion. Dr. James Bowman, a geotechnical engineer who studied karst foundation problems, has documented how solution channels in karst limestone allow what engineers call piping, water forcing its way through and carrying soil particles with it, creating larger and larger voids. This is how underground caverns grow. This is how sinkholes form. At Wolf Creek, this wasn't theoretical. It was happening, in real time, under 722 billion gallons of pressure. Every day the water was there, the limestone was dissolving. The Corps' first response was aggressive but temporary. From 1968 to 1970, they injected grout, a cement-like slurry, directly into the seepage channels. The grout hardens underground, filling voids and blocking water flow. It is like pouring concrete into a Swiss cheese to close the holes. The volume was staggering. Enough grout was pumped into Wolf Creek's foundation to pave a road 6 inches thick, 20 feet wide, and 5.5 miles long. Think about that. A road that stretches 5.5 miles. That is not a small repair. That is a massive remediation effort for a problem that was still brand new. That level of effort tells you everything about the scale of the problem. But grouting only stops water where it is currently flowing. It does not solve the underlying issue. Water, given enough pressure and enough time, finds new paths. And it did. Despite the grouting program, seepage continued. Engineers monitored it. The water kept finding routes around and possibly through the grout seals. Nature was more creative than the engineers anticipated. Something permanent had to be done, or Wolf Creek Dam would eventually fail. From 1975 to 1979, the Corps undertook what was supposed to be the definitive solution: a reinforced concrete cut-off wall. This wasn't just a patch. They drove concrete pilings 275 feet deep, deeper than the tallest buildings are tall, through the earth embankment and into the bedrock below. The wall stretched 3,800 feet long, composed of secant piles and rectangular panels, creating a physical barrier that water could not pass through. In theory, this was the answer. Water couldn't seep if there was a concrete wall blocking its path. The project was finished in 1979, and for a time, there was hope that Wolf Creek's seepage crisis had been solved. But the limestone underneath Wolf Creek Dam had other plans. The first cut-off wall, built from 1975 to 1979, had slowed the seepage, but it hadn't stopped it. In the decades that followed, monitoring systems detected something alarming. Seepage was increasing again. Water was finding new pathways around the cut-off wall, over it, under it. The karst geology wasn't just presenting one problem, it was presenting multiple problems, interconnected, shifting, evolving. The cut-off wall had slowed the seepage and reduced its speed, but it hadn't stopped it. Worse, engineers realized that if the cut-off wall had successfully blocked the main seepage channel, the water pressure behind it was building. That pressure would seek alternate routes, and alternate routes in karst limestone mean caverns, collapse zones, potential catastrophic failure points. It's like playing whack-a-mole with a giant mallet, and the mole has infinite holes. By the early 2000s, Wolf Creek Dam had been rated as one of the most dangerous dams in America, and the Army Corps of Engineers took the extraordinary step of placing it on the National Dam Safety Program's high-risk list. Picture this. You live in Burkesville, Kentucky, a town of about 1,700 people huddled along the Cumberland River just 5 miles downstream from Wolf Creek Dam. This is the first place the flood wall would hit if the dam failed. 5 miles. That's about 8 kilometers. In a car, it's maybe 10 minutes at highway speed. But if the dam fails catastrophically, there's no time for a car. You've got your house, your family, your job at the local store. You might not even think about the dam every day. It's just there, a part of the landscape. But the state handed out emergency warning radios to residents so they'd have maybe 5 minutes, if they're lucky, to get to higher ground. 5 minutes to gather what matters most and run. That's not a flood risk. That's Russian roulette. That's living under a sword of Damocles. And Burkesville is just the beginning. Further downstream, Salina, Tennessee sits directly below the dam's control point. It would feel the surge before Burkesville even fully understood what had happened. Nashville, Tennessee, a city of over 600,000 people, is positioned hundreds of miles downstream, where a catastrophic dam failure would send a surge of water powerful enough to cause $3.4 billion to $6 billion in damage. The estimated damage range? $3.4 billion to $6 billion. In 2007, the Army Corps of Engineers made a shocking public statement. Wolf Creek Dam presented an imminent risk of human life. Not eventually, not someday, now. Not in 10 years if nothing changes. Now. Imminent. That word carries weight. It means immediate danger. It means emergency. To manage this crisis, the Corps did something dramatic. They lowered the water level in Lake Cumberland, the massive reservoir behind the dam. A full lake puts full pressure on the foundation. The weight of all that water bears down on the limestone, increasing stress, creating pressure for water to find pathways through the rock. A lower lake reduces stress, buys time, reduces the probability of catastrophic failure. It's like releasing pressure from a balloon. But it also devastated the region's tourism and recreation economy. Lake Cumberland had become a vacation destination, with boating, fishing, and water sports generating millions in annual revenue. People planned vacations around Lake Cumberland. Families had beach houses there. Fishing guides made their living there. Marinas operated year-round. Lowering the lake level meant empty marinas, canceled vacations, abandoned boat ramps. The Corps was essentially saying, "We are destroying your economy to prevent a disaster." That's how serious they thought the problem had become. Then came 2013. After years of planning, the Army Corps of Engineers and a team of contractors, Trevicos and Solitanche, completed the most ambitious dam remediation project in American history. This wasn't a simple cut-off wall like the one from 1975. This was modern, state-of-the-art engineering. They built a new barrier system deep underground using 1,197 piles, each 3 feet in diameter, extending down to 275 feet into the bedrock. That's deeper than the tallest skyscraper in the world is tall. The wall stretched 3,800 feet long, almost 3/4 of a mile. The project cost $594 million, more than $500 million, and it was completed ahead of schedule in March 2013. To put that in perspective, that's roughly the entire annual budget of some small American cities spent on one dam. The construction method was revolutionary. They used technology that could precisely control the installation of secant piles and rectangular concrete panels, creating a geological seal that water couldn't bypass. Engineers believed this was the solution. The dam was saved, disaster averted, the limestone would be locked out, water would not find its way through. This was the permanent fix. But here's where the story gets truly alarming. Even after $594 million in repairs, even after the most advanced remediation techniques available in 2013, seepage continues. It's still there, still flowing, still finding paths. Monitoring systems at Wolf Creek Dam show ongoing seepage activity in the foundation. The seepage rates have been reduced, but they haven't gone to zero. Water still finds pathways through karst limestone, some of it around the remediation structures, some through cracks that form and reform in limestone, some following ancient solution channels that existed before the cutoff wall was installed. These are passages that have existed for millions of years, carved by water, ready to guide more water toward the dam. The dam doesn't leak like it did in 1968. The remediation has reduced the seepage significantly, but it hasn't eliminated it. And the question that keeps dam safety engineers awake at night is this: if water can still find a way through, what happens if the pressure increases? What happens if a major storm event leads to a full reservoir? What happens if the karst geology fails the remediation system in some unforeseen way? What happens if another seepage path develops that engineers haven't detected yet? How many more seepage routes are waiting in the limestone? Chris Stoltz, the project manager at the U.S. Army Corps of Engineers Nashville District, stated that the agency continues to monitor Wolf Creek Dam with advanced sensor systems. These sensors measure seepage rates, track changes in water pressure, detect movement in the embankment. If anything anomalous is detected, the Corps is prepared to lower the lake level again or take other emergency actions. But seepage monitoring is reactive. It responds to problems after they start. At a dam built on karst limestone, the real question is, can engineers ever truly know what's happening deep underground? How many seepage channels exist? How many have been remediated? How many are yet to be discovered? The sensors at Wolf Creek Dam are sophisticated, but they can only measure what they're positioned to measure. There could be seepage channels 500 feet underground that no sensor has detected because no sensor is placed there. There could be dissolution patterns forming in limestone that won't emerge as a problem for another 10 years. Engineers work with imperfect information about an invisible problem. They're trying to manage a disaster they can't fully see. That's the critical challenge of karst dam engineering. The 2022 contract awarded to American Bridge Company for the Wolf Creek Dam Spillway Gates Replacement Project, valued at $109.45 million, represents the most recent major infrastructure update to the dam. That's $109 million to replace gates. In June 2024, mobilization began on this project, with contractors installing access equipment and preparing to replace the spillway gates. These gates control water flow during extreme high water events. There are multiple gates, and they are heavy. Replacing them requires precision equipment, temporary supports, and engineering expertise. Newer gates with better hydraulic controls mean the Corps can manage the dam more precisely during flood season. More precise control during a crisis means better chances to prevent a catastrophic overflow. But here's the problem. Spillway gate replacement doesn't address the fundamental issue, the seepage. It doesn't fix the limestone. It doesn't eliminate karst. It's another band-aid on a structural challenge that may be permanent. It's maintenance. It's management. It's not a cure. And if you live downstream, you need to understand what that means. It means Wolf Creek Dam will always be a high-risk structure. It means the Army Corps of Engineers will always be managing this dam differently than they manage other dams. It means the region will always exist under a slightly elevated level of alert. The flood could come tomorrow. It could come in 20 years. Or it could be managed forever by engineers who understand the karst geology and respect its power. The residents of Burkesville, Salina, and the downstream communities don't get to choose. They get to wait. That is your life when you live 5 miles downstream from a leaking dam. The story of Wolf Creek Dam is, in many ways, the story of American infrastructure in the 2020s. We inherit massive structures built in the 1950s based on geological understanding that turns out to be incomplete. We discover problems that weren't visible until decades later. We spend billions trying to fix them. We hope our engineering is good enough, but we can never be completely certain. Veggent Dam in Italy failed catastrophically in 1963 because of a geological problem nobody anticipated. A mountain slope failure that sent a wave of water over the top of the dam, killing nearly 2,000 people. Teton Dam in Idaho failed in 1976 because its core was too porous. Water piped through it, just like at Wolf Creek. Banqiao Dam in China failed in 1975, and 171,000 people died. These disasters weren't acts of God. They were failures of engineering that couldn't account for the geological realities beneath the structures. At Wolf Creek Dam, the Army Corps of Engineers is trying desperately not to join that list. They have spent more than $750 million on this dam since 1968. On grouting, on cut-off walls, on sensors, on spillway gates, on remediation projects. $750 million. That's not a small investment. That's a massive commitment to preventing catastrophe. They lower the lake level when pressure builds. They monitor seepage continuously. They have emergency response teams trained and ready. Evacuation plans for downstream communities. Warning systems in place. Protocols established. But they also acknowledge, in their official documents and public statements, that Wolf Creek Dam remains high risk. They don't say it will never fail. They say they are managing the risk. And that's an honest position. Because in karst geology, you cannot eliminate risk. You can only manage it, moment by moment, decade by decade. You can only keep your fingers crossed and hope the limestone cooperates. The reality for communities like Burkesville is that you can never truly relax. You can never assume the dam is a solved problem. A representative from McCreary County, which borders Wolf Creek Lake, has stated that while the remediation has improved the situation significantly, the ongoing seepage monitoring continues. The county maintains emergency procedures. Schools have evacuation drills. Residents keep supplies. When you live downstream from a high-risk dam, emergency preparedness isn't paranoia. It's a fact of life. It's part of the social contract you sign by choosing to live in that area. You get water, you get flood control, you get cheap electricity, you get some tourism and recreation, but you also get monitored risk. You get sirens that could sound at any moment. You get the knowledge that in 5 miles upstream, 722 billion gallons of water are held back by a structure that engineers classify as dangerous. The economic impact of Wolf Creek Dam's seepage crisis is profound, and it's often overlooked in the debate about dam safety. Lake Cumberland was once a thriving recreation destination, generating roughly $50 million annually for the surrounding counties through boating, fishing, tourism, and hospitality. Think about that. $50 million every year flowing into small rural Kentucky communities. That money supports businesses, it employs people, it funds schools and infrastructure. When the Corps lowered the lake level in 2007 to reduce failure risk, that number dropped significantly. Marinas went under. Tourism declined. Families that had relied on seasonal tourism jobs for generations had to find other work. Property values near the lake fell. Nobody wants to buy a vacation home on a lake that's half full and could be drained further at any moment. The counties of McCreary, Pulaski, and Wayne, rural areas in southern Kentucky that depend on that tourism revenue, lost millions in economic activity. That's the hidden cost of a leaking dam. It's not just the potential for a catastrophic flood, it's the ongoing economic damage caused by the permanent state of reduced capacity. The dam cannot fill to its authorized level. The lake cannot reach its normal recreation stage. The region cannot capture its full tourism potential. And that loss continues year after year because of limestone that dissolves. Some experts question whether Wolf Creek Dam should continue operating at all. They argue that the cost of maintaining a high-risk karst dam, plus the lost tourism revenue, plus the ongoing risk to downstream populations, outweighs the hydroelectric benefits. Wolf Creek Dam generates about 270 megawatts of electricity, enough for roughly 200,000 households. That's significant power generation. But that power comes at the cost of perpetual risk management, $594 million remediation projects, and economic damage to the surrounding region. Alternative power sources, such as wind turbines, solar panels, natural gas generators, don't sit on unstable karst limestone. They don't threaten 25,000 downstream residents. They don't require 722 billion gallons of water held back by engineers' hopes and prayers. But decommissioning a 67-year-old major dam is politically complex, economically disruptive, and essentially never happens in America. Dams are permanent infrastructure. Once you build one, it's there. You cannot just take it apart. The environmental disruption would be massive. The economic displacement would be massive. The political resistance would be overwhelming. So Wolf Creek Dam remains, monitored, managed, leaking, waiting, for the next 50 years, maybe 100, until the limestone beneath Kentucky finally refuses to cooperate. The seepage at Wolf Creek Dam teaches us something uncomfortable about how we build in America. We build where the land is flat, where water is available, where geography seems ideal, without fully understanding what lies beneath. We build dams on limestone without fully understanding karst. We build bridges on compressible soils. We build cities on fault lines. We inherit these decisions from the 1950s and 1960s, when our knowledge was more limited and our caution was less developed. Geological surveys in that era weren't as detailed. Core samples weren't as sophisticated. Computer modeling didn't exist. Engineers made the best decisions they could with the information they had. And then, we spend the next 60 years and billions of dollars trying to fix what we didn't understand when we built it. That's not incompetence. That's the reality of human engineering. We work with incomplete information. We build anyway. We hope we got it right. And when we didn't, we spend the rest of the structure's life managing the consequences. Wolf Creek Dam is a monument to this cycle. Build, discover problems, spend money fixing them, manage risk forever. For the residents of Burkesville, that means keeping those emergency warning radios charged. It means knowing where you'll go if the sirens sound. It means living with the knowledge that 5 miles upstream, 722 billion gallons of water are held back by a dam that the U.S. Army Corps of Engineers officially rates as high risk for failure. It means understanding that your evacuation window is measured in minutes, not hours. 5 minutes, sometimes less. That's not enough time to pack a car full of memories. That's barely enough time to grab your family and run. It means accepting a level of disaster risk that most Americans never think about. Because while the dam is being managed, while the seepage is being monitored, While the engineers are doing everything they can, there's no absolute guarantee. There's only the hope that the remediation works, that the monitoring catches any new problems, and that the limestone beneath Kentucky's soil cooperates with the structures built above it. You can't negotiate with geology. You can't convince limestone to stop dissolving. You can only monitor it and hope. Wolf Creek Dam will likely never fail. The remediation works. The monitoring is advanced. The U.S. Army Corps of Engineers takes this seriously. Engineers have spent decades and hundreds of millions of dollars preventing disaster. But the fact that we need to have this conversation, the fact that a major American dam is officially classified as high risk for failure, the fact that 25,000 people live downstream in the zone of potential destruction, is a reminder that infrastructure failure is not an abstract concept. It's a reality that threatens real communities. It's not a natural disaster. It's an engineered structure whose failure would be catastrophic. And it starts in places like Burkesville, Kentucky, where the warning radios sit in homes, where residents know the dam is upstream, and where the limestone beneath continues to dissolve, one molecule at a time, in the darkness beneath the dam. The Wolf Creek Dam story is playing out in slow motion. It's a drama in which humanity built something extraordinary. A dam that controls a river, generates electricity, prevents floods. But in building that structure, we placed ourselves at the mercy of limestone. We built on unstable geology. We discovered the problem too late. And now we're locked into a permanent, expensive, anxiety-inducing relationship with that dam. We can't abandon it. We can't remove it. We can only manage it. And that's the choice we've made for the next generation of Americans who will live downstream, keep emergency radios charged, and hope the engineers got it right. When 25,000 people live downstream from a leaking dam, when infrastructure built a generation ago has become a permanent crisis for a region, grab your free disaster preparedness toolkit. The link is in the description. It walks you through evacuation planning, emergency supplies, and family communication strategies that could make the difference in any disaster scenario. Wolf Creek Dam might hold. The limestone might cooperate. The engineers might win this decades-long fight. But if they don't, if something fails, if seepage breaches the remediation, if karst geology has one more trick to play, having a real emergency plan isn't paranoid. It's survival. It's the difference between life and death. And that's the story America's dam engineers are hoping never ends the way they fear.